In this video, we're going to go over logarithms. We're going to talk about how to evaluate logs. We're going to discuss property of logs, expanding it, writing it as a single log, change of base formula, converting between exponential and log form. We're going to solve equations. We're going to work on some like word problems, compounded interest, and how to graph log functions and exponential functions. So let's begin. Let's start with evaluating logs. So log base 2 of 8 is equal to what number? What would you say? So 2 raised to the what power is 8? How many 2's do you have to multiply to get to 8? 2 times 2 times 2 is 8. So you need 3 2's to get to 8, because 2 raised to the third power is 8. So this answer is 3. Let's try another one. Log base 3 of 9. 3 to the what power is 9? We know 3 squared is 9. It takes 2 3's to get to 9. 3 times 3 is 9. So log base 3 of 27 is equal to what? How many 3's do you have to multiply to get to 27? We know that 3 times 3 times 3 is 27, so you need 3 3's. Log base 2 of 32 is equal to what number? How many times do you have to multiply 2 to get to 32? You need 5 2's. 2 times 2 times 2 times 2 times 2, 5 times is 32. Now what about log base 5 of 25? You need 2 5's. 5 times 5 is 25. So 5 squared is 25. Log base 6 of 36. We know 6 squared is 36. Now what about log base 2 of 16? What is that equal to? Feel free to pause the video and think about what the answer to that question is. 2 to the fourth power is 16. So the answer is 4. So if that's true, what is log base 2 of 1 over 16? 2 to the what power is 1 over 16? Well, I'll give you a hint. It's going to have a 4 in it, but it's not exactly 4. It's something else. This one is negative 4. You see, 2 to the 4 is 16, but 2 to the negative 4 is 1 over 16. When you have a negative exponent, it flips the fraction. So instead of 16 over 1, you get 1 over 16. Now what about this one? Let's say if we reverse the order. So log 16 of 2 instead. So like all of them, it's going to have a 4 in it. But what do you think the answer is? It turns out that it is 1 over 4. 16 to the 1/4 power, which is the same thing as the 4th root of 16, is equal to 2. Now what about this one? Log base 16 1 over 2. What is that equal to? Now this answer is simply negative 1/4. So when you see that whenever this is a fraction, it's negative, as you can see. And whenever this number is larger than the 2, it's a number that's bigger than 1, not including negative signs. So you get like an integer. Whenever this number is smaller than this one, you get a fraction. 2 is smaller than 16. Same thing here. 2 is smaller than 16. We're not looking at the fraction, just the 2 part. But we get a fraction. Let's try another example like that. So let's use log base 2 of 8. We know it's equal to 3. So log base 8 of 2, if we reverse it, it's 1/3. Log 2 of 1 over 8 is negative 3. And log 8 of 1 over 2 is negative 1/3. There's going to be a 3 somewhere. So maybe at this point you see the pattern. So remember, whenever you have a fraction here, it's negative. And whenever this number is smaller, it's a fraction. Okay, so let's move on to some other examples on evaluating logs. So what about this one? Log of 10. What's the answer for that? Now, if you don't see a base, it's always base 10 if it's not there. So 10 to the what power is 10? It turns out 10 to the 1 is 10. Now what about log of 1? Log of 1 is always 0, regardless of what the base is. But we know the base is 10. 10 to the 0 power. Anything to the 0 power is a 1. Now what about log of 10 to the 5th? We know it's base 10. 10 to the 5 is 10 to the 5, so the answer is 5. Another technique that you could do is you can move this 5 to the front. So it's 5 log 10. We know log 10 is 1, so 5 times 1 is 5. So what about log 1,000? 1,000 is basically 10 to the 3rd power. You need 3 zeros. And then move the 3 to the front. So you now have 3 log 10, which is 3 times 1, so that is 3. So log of 100,000, 1 million actually, you see that you have 6 zeros, so it's going to be 6. Log of 100 has 2 zeros, so it's going to be 2. Log of 10,000 has 4 zeros, so that's like log of 10 to the 4, so it's going to be 4. Log of 0.001, that's basically log 10 to the minus 3, which is negative 3. If your answer is between 0 and 1, it's negative. Log of 0.1 is negative 1. Log of 0.01 is negative 2. Log of 0.0001 is negative 4. Log of 0.00001, that's negative 5. Hopefully you see a pattern at this point. Log of 0 does not exist. Something you should know. And log of like negative 4 or any negative number also does not exist. Now what about this one? Let's say if we had a square root. Log of base 2 square root of 128. What would you do in this case? You need to know that the 128 is raised to the 1st power. And for square roots, if you don't see a number here, there's a 2. So we can rewrite this as log base 2, 128 raised to the 1/2. And we can move the 1/2 to the front. So therefore we have 1/2 log base 2, 128. 2 raised to the what power is 128? How many 2's do we have to multiply to get to 128? 2 times 2 times 2, that's 8 so far, times 2 times 2 times 2, that's another 8. 8 times 8 is 64, times 2 is 128. So we need 7 2's to get to 128. So log base 2 of 128, that is 7. So 7 times 1/2 is equal to 7 over 2. That's the answer for this expression. Let's try another one. Log base 3 square root of 27. So that's log base 3 of 27 raised to the 1/2. And we're going to move that 1/2 to the front. So 1/2 log base 3 of 27. 3 to the what power is 27? 3 to the 3rd. You need 3 3's to multiply to get to 27. So this is 3 over 2. That's the answer. And for our final example, log base 3 cube root of 81. This is log base 3, 81 to the 1/3. Move the 1/3 to the front. Then how many 3's do you have to multiply to get to 81? 3 times 3 is 9. And another 2 3's gives us 9. 9 times 9 is 81. So we need 4 3's to get to 81. So log base 3 of 81 is 4. So our answer is 4/3. So let's talk about some other properties of logs. We've already discussed this one. Log base A of B is equal to B log A. You've seen that property used already. Now also another one that we have, log base A plus log base B is equal to log A times B. So we can condense two logs into a single log by multiplication if they have a positive sign. Now let's say if it's subtraction, log A minus log B, this will become a single log, but it's going to be log A divided by log B, or just B, log A divided by B. So log A has a positive sign in front. Because it's positive, it goes on top. Log B has a negative sign in front of it. So anything with a negative sign goes in the bottom. So now let me show you how to apply this information. This information is useful, particularly when you have to expand or condense into a single log. Let's focus on expanding into a sum and difference of logs. So let's say if we have log x squared, y cubed, z to the fourth. So everything is multiplied. That means we could separate it by addition. So this is equal to log x squared plus log y cubed plus log z to the fourth power. Next, all of the exponents we're going to move to the front. So our final answer for this problem is 2 log x plus 3 log y minus 4 log z. Let's try another example. So let's say if we have log x to the fifth y squared z to the third r to the sixth power. So every term that's on top is going to be positive, and the ones on the bottom is going to be negative. So we have positive log x to the fifth plus log x y squared. Z's in the bottom, so minus log z to the third minus log r to the sixth, because r is in the bottom as well. Next, every exponent we're going to move to the front. So 5 log x plus 2 log y minus 3 log z minus 6 log r. That's it for that problem. So now let's throw in some square roots, some radicals. Let's make it a little bit more challenging. So let's say if we have log cube root of x squared y to the fifth z to the fourth. Now remember, this radical encompasses everything. Now the first thing I would do is rewrite it as log x squared y to the fifth over z to the fourth, but raised to the 1/3. And then just move the 1/3 to the front. So now we have 1/3 log x squared y to the fifth z to the fourth. Now we can expand it into a sum and difference of logs. So we're going to keep the 1/3 all the way in the front. It's going to be distributed by everything. So we have 1/3 log x squared plus log y to the fifth. Z is in the bottom, so minus log z to the fourth. So now we're going to move the exponents to the front. So now we have 1/3 2 log x plus 5 log y minus 4 log z. That's our answer in factored form. If you want, you can distribute the 1/3 to every term inside it. So let's just go ahead and do that. So we can also write the answer as 2/3 log x plus 5/3 log y minus 4/3 log z if we want to. Both forms are acceptable. So for our final example for expanded logs will be this problem. Log 5th root of x cubed y to the 4th. So notice that the radical doesn't affect everything. So at this point, we can go ahead and separate it, but let me change the radical first. This is the same as x to the 3/5 and then y to the 4th. So let's expand it. So now it's log x to the 3/5 because that's on top. The y is on the bottom, so minus log y to the 4th. Then move the exponents to the front. So 3/5 log x minus 4 log y. That's it. So now, let's try the reverse. Let's work on combining it into a single log. So let's say if you have 3 log x minus 2 log y plus 1/3 log z. So first, move the coefficients back to the exponent position. Put them on top of each variable. So now we have log x cubed minus log y squared plus log z to the 1/3. And then combine it to a single log. So this has a positive sign, it's going to go on top. This is negative, it goes on the bottom. That's positive, it goes on top. So write just one log, that's it. Then put a big fraction. So we have x cubed on top times z to the 1/3, and then y squared on the bottom. Now we could leave the answer like this. Now we have a fraction here, we can convert that to a radical form if we wish. But the 1/3 only affects z. So there'll only be a cube root for z. So it's going to be x cubed, cube root z over y squared, all within one single log. Now I'll try only one more example for that type of problem. So 1/4 log x minus 5/4 log y plus 3/4 log z. Now at this point, we can factor out a 1/4, but we don't have to. We could do it now or later, but let's do it later. So let's move this to the front, every coefficient. So we have log x to the 1/4 minus log y to the 5/4 plus log z to the 3/4. By the way, feel free to pause the video and combine it into a single log and see if you can get the answer as well. But let's continue. So now we're going to write one single log and a fraction. So the first one, we have positive log x, then negative, and then positive. So x and z will be on top again. So x to the 1/4, and then z to the 3/4 divided by y to the 5/4. Now what I'm going to do is factor out 1/4 from every exponent. So I can write log x to the 1, z to the 3. Notice that the numerator stays, y to the 5. Here's a 1, here's a 3, here's a 5. You can do this if they have a common denominator, which is they do. And then all raised to the 1/4. And then move that 1/4. Well, you could move it to the front, but you don't have to. But what we could do is we could turn it into a radical. In this case, the 4th root. So we could say this is the 4th root of x. X to the 1 is just x. Z cubed, and then y to the 5th. We can write that as a final answer. So whenever you have fractions, you can convert it back to radical form. So that concludes that example. Now let's talk about the change of base formula and how to use it. Now earlier we said that log base 2 of 8 is 3. Here's the change of base formula. Log base a of b is equal to c. You can also do this. Log of b divided by log of a is also equal to c. That's the change of base formula. This new base x could be anything. It could be 12, 5, 24. It doesn't really matter. Whatever you want it to be, it can be it. So, in your calculator, if you want to find out what log base 2 of 8, type this in. Log 8 divided by log 2. You can also get 3 as well, if you don't want to do it in your head. So, let's say if we wish to figure out what log base 5 of 100 is. Simply type in log 100 divided by log 5. And you should get about 2.861. You see, for this, we can't do it in our head. We have to use the calculator. And that's how you type it in, log 100 over log 5. Now, sometimes they may want you to write, let's say, a log in terms of a natural log. Let's say you have log base 2 x squared y cubed. You can write it as a natural log by doing this. ln x squared y cubed over ln 2. Use the change of base formula. So like log base 3 of 8, we can say it's log 8 over log 3, or we can write it as a natural log, ln 8 over ln 3. That's how you can convert a log into a natural log, by using the change of base formula. By the way, if you're wondering what's the difference between log and natural log, they're very similar. Whenever the log has a base e, it becomes a natural log. That's it. The natural log is specific. The base of any natural log is always e. That's what's special about it. If you want the base to be anything else but e, you have to use the word log. If it's base e, then by definition it's a natural log. So if you see ln x, there's an invisible base e that you don't see, just so you know. So logs and natural logs, they're exactly the same. They only differ in a base. ln has the base e. All the properties are exactly the same. Now sometimes you'll see a question that would say, convert this into log form. How would you do it? Here's the formula that you want to use. Log base a of b is c. A raised to the c power is equal to b. So a raised to the c is equal to b. You want to use that formula to convert it. So log base 3 of 81 is equal to 4. A is the 3, the 4 is the c, b is the 81. As you can see, 3 to the 4th power is equal to 81. Let's try another example. Try this one. 5 to the 3rd is equal to 125. Write it or convert it to logarithmic form. So log base 5 of 125 is equal to 3. As you can see, 5 raised to the 3rd power is equal to 125. So let's try 2 more examples. So feel free to pause the video and convert the following into logarithmic form. So log base 2 of 8 is equal to 3. Let's check it. 2 raised to the 3rd power is equal to 8. So here this is going to be log base 4 of 16 equals 2. The exponent is always on this side, as you can see. It's always across the equal sign. So to check it, 4 raised to the 2nd power is equal to 16. So now let's work on converting to exponential form. Let's try these 2 problems. Log base 3 of 9 equals 2, and log base 3 of 243 is equal to 5. So to change it back to exponential form, it's going to be this: 3 to the second power is equal to 9. For this one, 3 to the fifth power is equal to 243. And let's just try two more examples. Why not? Try these. Log base 7 of x is equal to 3, and log base 7 of 49 is equal to 2. So 7 raised to the third power is equal to x. And here, 7 to the second power is equal to 49. And that's it. That's how you can convert a logarithmic equation into its exponential form. So now let's work on solving log equations. We're going to cover the different types of equations that you may see on your test. So let's start with this one. Log base 5 of 10x minus 5 is equal to 2. When you see one single log equal to a number, convert it into its exponential form. 5 to the second power is equal to what's inside. So 5 squared is equal to 10x minus 5. 5 squared is 25. Then add 5 to both sides. So plus 5 plus 5. So now you have 30 is equal to 10x. Next, divide both sides by 10. So 3 is equal to x. And that's the answer. Also, when you get your answer, plug it in. Make sure you don't get any negative values. Because if you get a negative value, it doesn't work. It's no solution. Let's try another example. Natural log square root x minus 8 is equal to 5. Now this natural logs have a base e. So for this one, it's e raised to the fifth is equal to what's inside. Now to get rid of the radical, we're going to square both sides. So when you raise one exponent to another, you multiply it. So we have e to the 10. 5 times 2 is 10. The square and the radical will cancel. So we have x minus 8. Then all we got to do is add 8 to both sides. So x is e to the 10 plus 8. And you can type that in your calculator and get the decimal value for that. Let's try some other examples. Let's say if we have this log base 3 of 5x plus 2 is equal to log base 3 7x minus 4. Notice that the bases are the same. What this means, therefore, that these two expressions must be equal to each other. And so we can say that 5x plus 2 is equal to 7x minus 4. And then solve for x. So let's subtract both sides by 5x. And simultaneously, let's add 4 to both sides. So that cancels, that cancels. So we have now 6 is equal to 2x. And then divide both sides by 2. 6 divided by, that was supposed to be a 2. 6 divided by 2 is 3. So x is 3. Try this example. Log base 2 x minus 1 plus log base 2 x plus 1 is equal to 3. Feel free to pause the video and try it yourself. So now let's begin. What we need to do is, notice that we have a number on the right side and 2 logs on the left. We want to combine the 2 logs into a single log. And because they both have a positive sign in front of them, it's going to be multiplication instead of division. So it's log base 2 and then x minus 1 times x plus 1 is equal to 3. So now we can convert it back to its exponential form. 2 to the third power is equal to what's inside. So 2 to the third is equal to x minus 1 and x plus 1. So we can FOIL those two terms. And if we do so, it's going to be x squared minus 1 is equal to 8. So we're going to add 1 to both sides. So 9 is equal to x squared. And then square root 9. So x could be plus or minus 3. Now, positive 3 works. But negative 3 doesn't work. X cannot equal negative 3. Here's why. If we plug in negative 3 minus into x, we'll get negative 3 minus 1, that's a negative 4. A log base 2 of negative 4 doesn't exist. If you plug in a negative number, it doesn't work. So this one's no solution. We only get one answer. In this case, 3. So now let's try this example. Log base 3 8x plus 3 minus log base 3 of x is equal to 2. So try this example. So now that we have a subtraction sign, it's going to be division instead of multiplication. So this one is positive, so this is going to go on top. So 8x plus 3 divided by x is equal to 2. So let's convert it to its exponential form. 3 to the second power is equal to what's inside. 3 squared is 9, but I'm going to write it as 9 over 1. Whenever you have two fractions separated by an equal sign, cross multiply. So 9 times x is 9x. Don't forget the equal sign. And then 8x plus 3 times 1 is just 8x plus 3. So let's subtract both sides by 8x. So that cancels. 9x minus 8x is 1x. So 1x is equal to 3. That's the answer. So now let's try this example. Log base 2 of x plus log base 2 x plus 5 is equal to log base 2 x plus 4. So we have 3 logs. Let's combine this into a single log. So because they're separated by addition, we're going to combine them by multiplication. So we can distribute this x into the x plus 5. So it's x squared plus 5x. And that's equal to log base 2 x plus 4. So because the bases are the same, we could set these two equal to each other. So x squared plus 5x is equal to x plus 4. Notice that we have an x squared and an x to the first power. That means this is a quadratic. We may have to factor it. So let's move everything from the right side to the left side. So now we have x squared. 5x minus x is positive 4x. And we have negative 4 as well. So let's continue this on the... Actually, we could finish this on this page. We can factor this. It's going to be two numbers that multiply to negative 4 but add to positive 4. Negative 2 and negative... No, that doesn't work. This expression can't be factored. We may have to come up with another way of solving it. Let's see, x squared plus 4x minus 4 is equal to 0. We may have to use the quadratic equation, which is negative b plus or minus square root b squared minus 4ac over 2a. So this is a, this is b, this is c. So b is 4, a is 1, and c is negative 4, divided by 2a. If it was x squared plus 4x plus 4, we could have factored it as like x plus 2 times x plus 2. But two numbers that multiply to negative 4 but add to positive 4, that doesn't work. But we can still figure it out. So negative 4 plus or minus 4 squared is 16. Negative 4 times negative 4, that's 16. So here we have the square root of 32 over 2. The square root of 32 can be broken down into root 16 times root 2. And the square root of 16 is 4. So we get 4 root 2 divided by 2. So our answer is negative 2 plus or minus 2 root 2. So we have two answers. Negative 2 plus 2 root 2 and negative 2 minus 2 root 2. So at this point I'm going to use the calculator and see what the decimal values are. For this, I got about 0.828, and for the other one, negative 4.828. Now, the reason why I'm doing that is because I want to see which answers work and which ones do not work in the original expression. Notice that positive 0.8 works. None of these values will be negative. But if we plug in negative 4.8 into x, we're going to have a negative inside of a log, and that doesn't work. So this is our answer. Okay, so now let's try another example. 4 raised to the 2x minus 1 is equal to 8 raised to the 3x plus 2. How would you solve for x? Now for this one, we don't need to use logs to solve this particular problem, because 4 and 8 have a common base, that's 2. 4 can be replaced with 2 squared, because 2 squared is equal to 4. And 8 can be replaced with 2 to the third power, because 2 times 2 times 2 is 8. But these exponents are still here. Whenever you raise one exponent to another exponent, you multiply it. And that's a 1 right there. So we need to distribute this 2 to the 2x minus 1. So it's going to be 2 raised to the 4x minus 2. And we're going to do the same for this expression. 3 times 3x plus 2, that's 9x plus 6. Now that we have the same base, we can therefore set the exponents equal to each other. So 4x minus 2 is equal to 9x plus 6. So we're going to add 2 to both sides and subtract 9x from both sides. So negative 5x is equal to 8, and x is 8 over negative 5. Now for exponents, you can have negative values in the exponent. For example, 3 to the 2 is 9, and 3 to the negative 2 is simply 1 over 9. So there's no issues with negative answers here. Let's try this one. So 9x minus 2 is equal to 27 1/3 x minus 4. So feel free to pause the video and try the problem yourself. So 9 and 27, they share a common base, base 3. 3 squared is 9. 3 to the third power is 27. So now we need to multiply the exponents. So here we have 3 to the 2x minus 4 is equal to 3. 3 times 1/3 is simply 1. So this is just x minus 12. So now we could set 2x minus 4 equal to x minus 12. So I'm going to subtract the x from both sides. That's going to cancel. And then I'm going to add 4 to both sides. So 2x minus x is x. And negative 12 plus 4 is negative 8. So that's the answer. So now let's say if you have an exponential equation where you can't convert it to the same base. What do you do in a situation like this? How do you figure it out? You can take the log or natural log of both sides, but I'm going to take the natural log because less letters to write, so I'm going to do that. So after you take the natural log of both sides, move the x to the front. So x ln 5 is equal to ln 8. Then divide both sides by ln 5. So you get x is equal to, so let me go ahead and get the decimal value of that answer. So ln 8 divided by ln 5, you should get about 1.292. Now what about this particular problem? Let's say if you have 3 to the 2x plus 4 is equal to 7x minus 3. Now you know we need to take the natural log of both sides, but I think you should try this problem because there's a lot more work involved. So what we're going to do is move the exponents to the front. Now when you do it, it has to be in parentheses because the 2x plus 4 is distributed by the ln 3. Next, distribute the ln 3. So we have 2x ln 3 plus 4 ln 3 is equal to x ln 7 minus 3 ln 7. Now your goal is to get x by itself. So every term that has an x, let's move it to one side. In this case, the left side. And any term that doesn't have it, let's move it to the right side. So it's going to be 2x ln 3. And if we take this term and move it here, it's going to be negative x ln 7 is equal to. Now we're going to take this term, move it to that side. So it's negative 4 ln 3 minus 3 ln 7. So now what we're going to do is factor out x because we have a common term. So if we take out x, what we're going to have left over is 2 ln 3 minus ln 7, and that's equal to what we see here, which I'm just going to put quotations. Next, we're going to divide it by this term. So x is equal to negative 4 ln 3 minus 3 ln 7 divided by 2 ln 3 minus ln 7. So this is much more work for this example. And then you just got to type that in your calculator and get the answer. So now let's solve for x dealing with base e problems. If you see a base e, take the natural log of both sides. So ln e to the 2x is equal to ln 7. Now these are a little bit easier. We can move the 2x to the front. The reason why they're easier is because ln e is equal to 1. So therefore 2x times 1 is simply just 2x. And that equals ln 7. So divided by 2, x is ln 7 over 2. And then you can get the decimal value for that answer if you want. So let's try this problem. E to the 4x minus 5 is equal to 3. So we're going to start by taking the natural log of both sides. And we're going to move this to the front. So 4x minus 5 times ln e, which will become 1, is equal to ln 3. So let's add 5 to both sides. So 4x is ln 3 plus 5, then divide by 4. So ln 3 plus 5 over 4 is the answer. And as a decimal, that is equal to 1.5247. Try this problem. E to the excuse me, e to the 2x minus 4, e to the x minus 5. How would you do that problem? The best way to solve it is by using substitution. We're going to replace e to the x with y. So then this becomes y squared minus 4y minus 5 is equal to 0. So this we can factor. Two numbers that multiply to negative 5 but add to 4. Add to negative 4. It's negative 5 and positive 1. So we can write this as y minus 5 and y plus 1. So therefore, y is equal to 5 and y is equal to negative 1. You set this term equal to 0 separately, and then this term equal to 0. So if y plus 1 is equal to 0, and you move the 1 to the other side, y is equal to negative 1. So at this point, replace y with e to the x. So e to the x is 5, and e to the x is negative 1. Now I need to take the natural log of both sides. So ln e to the x is equal to ln 5. Move the x over here. So x ln e is ln 5. Ln e is 1, so x is equal to ln 5. And here, it's going to be the same thing. X is equal to ln negative 1. But you can't have a negative inside of logs or natural logs, so there's no solution here. So the answer for this problem is simply x is equal to ln 5. Now our final example relating to solving equations will be this problem. Let's try this. 525 and divided by 1 over e to the negative x is equal to 275. How would you solve a problem like this? What I would do is put this over 1 and then cross multiply. So 525, if we multiply these two, is equal to the multiplication of those two terms. 275, 1 e to the negative x. 1 plus e to the negative x. Now what I would do is divide both sides by 275. And so 525 divided by that number, I got 21 over 11, or 1.90909. But I'm going to keep it as a fraction. So next I'm going to subtract 1 by both sides. By the way, 525 and 275 are divisible by 25. If you divide each one by 25, that's how you can get 21 over 11. So now 21 over 11 minus 1 is equal to e to the negative x. And 1 is the same as 11 over 11. So 21 minus 11 is 10. So we have 10 over 11 is equal to e to the negative x. So take the natural log of both sides. And then move this negative x to the front. So ln 10 over 11 is equal to negative x ln e, but ln e is 1. So if we move the negative sign over here, we get x is equal to negative ln 10 over 11. Now we can do something. We can put the negative sign into the fraction. Let me show you. So we can leave our answer like this. X is equal to negative 11, 10 over 11. Or, remember there's a negative 1 here. We can move it over here to this position. So that's positive ln 10 over 11 raised to the negative 1. Meaning this whole fraction is raised to the negative 1. So that's the same as 11 ln 11 over 10. And that's our final answer. And as a decimal, it's about 0.0953. 1. And that's positive, by the way. So next we're going to focus on graphing equations. So let's say if you want to graph an exponential equation, y is equal to 2 raised to the x plus 1 minus 3. How would you do it? Now, the first thing I will look at is this number, negative 3. That is going to be your horizontal asymptote. Exponential equations have horizontal asymptotes. Logarithmic equations have vertical asymptotes. So we have one at negative 3. Now, I would make a table for this type of problem. You want to plug in two numbers for x. And I'm going to show you how to find those two numbers. Whatever exponent you see here, set it equal to 0 and 1. So you want to plug in negative 1 for x. This is supposed to be a 1 here. And 0 for x. If you do that, you're going to make your life so much easier when graphing these problems. So if we plug in 0 for x, 0 plus 1 is 1. 2 to the first power is itself 2. And then 2 minus 3 is negative 1. So we're going to get negative 1 here. And if we plug in negative 1 for x, negative 1 plus 1 is 0. 2 to the 0, or anything to the 0 power, is 1. 1 minus 3 is negative 2. And then plot those 2 points. So 0, negative 1, that's over here. And then negative 1, negative 2 is right here. So when you graph it, start from the asymptote and then follow the function. So it looks like that. You can add another point if you want. You can plug in 1. And let's see, that's 1 plus 1 is 2. 2 squared is 4. Minus 3, that's 1. So when x is 1, y is 1. But my graph is not, perfectly accurate, but I just want to give you some general guidelines to graph it. Now here's why choosing those points will be helpful. Let's say if you have to plot this. Let's say 1/3 x minus 4 plus 1. So first plot the horizontal asymptote, which is this number. It's at 1. Next, choose the values that you want to pick. In this case, 2 points. To find those 2 points, whatever this is, set it equal to 0 and 1, and then solve for x. So the 2 points that you want is x is equal to 4 and x is equal to 5 if you add 4 to both sides. So this is going to be 4 and 5. Now if we plug in 4, 4 minus 4 is 0. 1/3 to the 0 power is 1. Anything to the 0 power is 1. So less math work for us. And hold on, we got to add this 1 as well. So we actually get 2. Now to get the next point, let's plug in 5. 5 minus 4 is 1. So 1/3 to the first power is 1/3 plus 1. 1/3 is about 0.33. And if we add 1 to that, that's about like 1.33. So now we can plot this graph. So 1, 2, 3, 4, 5. When x is 4, y is about 2. So it's somewhere over here. And when x is 5, it's about 1.33. So over here. So with those 2 points, we can see that if we start from the horizontal asymptote and follow those 2 points, the graph is going like this. And as long as you have those 2 points in the asymptote, you know which direction you're going to go. Just start from the asymptote and follow the points. So now we're going to work on a different type of exponential function, one dealing with base e. So let's say e x minus 2 plus, actually, let's do minus 4. So let's start with the horizontal asymptote, which is at -4. And then let's make our table. Same rules apply here. Now we're going to set x minus 2 equal to 0 and 1. So the numbers that we want to choose are 2 and 3. So if we plug in 2 for x, 2 minus 2 is 0, and e to the 0 is a nice number, which is 1. And then 1 minus 4, don't forget that number, is -3. -3 is a nice number to plot. Now if we plug in 3, 3 minus 2 is 1. So e to the 1, you need to know that e is about 2.7. So 2.7 minus 4, -1.3. If you pick these two values, like if you use this process to get these two values, for all e functions, you're going to get e to the 0 and e to the 1. It's always going to work that way because you set it equal to 0 and 1. And e to the 0 will always be 1. E to the 1 is just 2.7. And just using those two numbers, this problem becomes doable. You can do it. Okay, so now let's plot our points. When x is 2, y is -3. And when x is 3, y is about -1.3, which is between -1 and 2. So somewhere in this area. I believe I graphed that correctly. So now start with the asymptote and then follow the points. And that's the general shape for your graph. So that's how you graph exponential functions. Now you know how to find the asymptotes. And the one thing I forgot to mention is the domain and range. So let's do it for this problem. The domain for all exponential functions is simply -infinity to infinity. X could be anything. So that's half the battle. The range is where it's important. The range, look at the y values. The lowest y value is at -4. The highest y value is infinity. So the range starts from -4 to infinity, but it doesn't touch the horizontal asymptote, so this has to be parentheses and not bracket. So let's quickly review the other examples that we had. There was one example where I'm just going to do a quick sketch. The asymptote was -3, and basically the graph was like this. The domain for that function, I think it was 2x plus 1 minus 3. The domain is always going to be the same, -infinity to infinity. The range, it starts from the asymptote, which is basically that number, and it goes to infinity. Now keep in mind, you can get a graph that looks like this. Let's say asymptote is over here at +2, and you get a point like here and another point here. If you graph it starting from the asymptote, this is going down. So going from bottom to top, the range is going to be different. The lowest y value is -infinity and the highest is 2. So your range is, it looks like it's in reverse. So watch out for those problems as well. The domain is going to be the same. It's all real numbers. So now let's talk about how to graph logarithmic functions. So let's try this example, log base 2, x minus 1 plus 3. So logarithmic functions, they have vertical asymptotes as opposed to horizontal asymptotes. So here's what you want to do. Whatever is on the inside, set it equal to 3 numbers instead of 2 numbers. The first number you want to set it equal to is 0. This is going to give you your vertical asymptote. The next one you want to set it equal to is 1. And the next number is whatever this number is, the base. In this case, 2. So your vertical asymptote is x is equal to 1. And then your points are x is equal to 2 and x is equal to 3 for this particular example. So let's plot the vertical asymptote, which is at x is equal to 1. So it looks like this. Now let's make our table. So we're going to plug in 2 and 3 into the table. So if we plug in 2, 2 minus 1 is 1. So we have log of 1. Log of 1 is always 0. Always. Regardless of what the base is. And that's why I chose to do it that way. And then simply add this number. So 3. Now if we plug in 3, 3 minus 1 is 2. Log base 2 of 2 is always going to be 1 because these two, they match. That's why this number is always this number. So log base 2 of 2 is 1, then add 3 to it, we get 4. And now we can plot it. So when x is 2, y is 3, and when x is 3, y is 4. So you start from the asymptote and follow your 2 points, so it goes like that. And that's how you graph it. So now let's talk about the domain and range before I forget. The range is all real numbers for logarithmic functions. As you can see, it starts from the bottom and it keeps going up. So when you look at the range, look at the lowest y value to the highest y value. But for logs and natural logs, it's always the same. Now, for the domain, it's different. You need to view it from left to right. This graph, it starts at 1. That's the lowest x value. The highest x value is positive infinity. So it's from 1 to infinity. Let's try another example dealing with logs. So let's say if we have log base 3 x plus 4 minus 2. So x plus 4, we're going to set it equal to 3 numbers. 0, which is going to be the vertical asymptote. We're going to set it equal to 1. And we're going to set it equal to whatever the base is, in this case 3. So the vertical asymptote is x is equal to -4. That's our VA. And our first point is at -3, and our second point is 3 minus 4, that's -1. So let's plot the vertical asymptote. So it's at -4, and there it is. And let's put our points into this equation. So if we plug in negative 3 for x, negative 3 plus 4 is 1. Log base 3 of 1, log of 1 is always 0. So 0 minus 2 is negative 2. Now, if we plug in negative 1, we have negative 1 plus 4 is 3. So log base 3 of 3 is 1 because those two numbers, they cancel. Then 1 minus 2 is negative 1. And then plot those numbers. So at negative 3, we're at negative 2 on the y-axis. Well, not on the y-axis, but going down 2. So then the next point is at negative 1, and then down 1, which is over here. So starting from the asymptote, we're going to follow those 2 points. So the range is going to be the same. It's our real numbers, negative infinity to infinity. Now the domain, it starts from negative 4 and it stops at positive infinity. View it from left to right. So it's negative 4 to infinity. It's based on whatever the vertical asymptote is. And for the exponential function, the range is based on the horizontal asymptote. So that's it for graphing functions. Now let's talk about solving word problems as it relates to logs and exponential equations. So let's say if you have a problem that has these keywords: compounded monthly, weekly, daily, annually, semi-annually, compounded anything but continuously. Use this equation. So let's say if you have a problem where you invest, let's say $5,000, and the interest rate is 8%, and let's say it's compounded monthly. How many months are in a year? 12 months. So if it's compounded monthly and it's 12, that means your account is going to be credited interest each month in the year, so 12 times a year. N is the number of times that you receive interest per year. So P is your principal, that's your initial investment, that's 5,000. R is your interest rate, but as a decimal. So 8% divided by 100, and you get 0.08. And that's what you want to plug in for R. N is 12. And let's say we want to find out how much will be in the account after 7 years. T is the time in years, so 7 in this example. And then in your calculator, type it exactly the way you see it. So 5,000, and then okay, you should get this answer. Now, because we're dealing with money, you want to round it to the nearest hundredth. So it's $8,737.11. That's how much will be in account after 7 years. So now, let's try another example where we want to find the initial investment. So let's say if the interest rate is 7%, actually let's say 7.5%. Let's say it's compounded weekly. How many weeks are in a year? It turns out 52. If they say compounded semi-annually, that's 2, and it's 2. Quarterly, there's 4 quarters in a year, and it's 4 for quarterly. Monthly, and it's 12. There's 52 weeks in a year, so for weekly, and it's 52. Daily, and it's 365. So let's say that you have an account that credits you 7.5% interest, and it credits you, this is the annual interest rate, but it breaks it down, it credits you every week. And let's say you want to find out how much is in the account after 8 years. And you want to find out, actually, you want to find out what initial investment you need to put in so that after 8 years you have a final amount of 10,000. Okay, yeah, because I want to rephrase this problem where you have to solve for the initial amount. So how much money do you have to put in if you want your account balance to be 10,000 after 8 years if you receive a 7.5% interest rate and your account is credited weekly? So because this is your final amount, A is 10,000. You want to solve for your principal. your principal investment, how much you have to put in at the very beginning. That's P. So to find out what R is, divide it by 100 or move the decimal point 2 units to the left. So R is 0.075. N is 52, and we want to find out how much it is, or the time is 8 years, basically. That's what I'm trying to say. So now, how would you solve for P in this problem? What I would do is first figure out what all of this is equal to. So 1 plus 0.075 divided by 2, all in parentheses, raised to the 52 times 8. It's raised to that power. And this entire expression, if you type that in your calculator, you should get 1.82133. At least that's what I got. So now all you got to do to solve for P is divide 10,000 by this number. And then, so your principal investment, how much you need to put into the account is $5,490.49. By the way, we said that for daily, N is 365. And for weekly, N is 52. And for annually, N is just 1. But what if your account is credited every 2 years instead of every 1 year? If it's credited every 2 years, N is 1/2. Let's say if it's credited every 5 years, N is 1/5. If it's credited twice a year, N is 2. That's semi-annually. Do you see a pattern here? If it's credited every 8 years, N is 1/8. So just in case you get some rare problem that states something like that, that's what you can do for that situation. Now the next question, let's say if it's compounded continuously, keyword continuously, you want to use A equals PERT. So let's say your initial investment is $5,000 and it's compounded continuously at an interest rate of 8%. What's going to be in the account after 4 years? So P is your investment, your initial investment, and R, 8 divided by 100 is 0.08, and then T is 4 years. And then just type that in. So you should get 6,885 and 64 cents. So let's say if we want to figure out how long it takes your account to double if your interest rate is 9%. So you want to find out T. What I would do is plug in P for 1 and A for 2. You could plug in 1,000 for your investment and 2,000 for your final amount. But if you do 2,000 over 1,000, you're going to get 2 anyway. So I would set it up like this. And then R is 0.09. So we got to solve for T. So take the natural log of both sides. And then take this term, move it to the front. So we have this. ln is 1, so that disappears. So all we got to do is divide by 0.09. So ln 2 divided by 0.09, that's going to give us T. And you're going to get about, T is about 7.7 years. That's how long it's going to take your account to double if it's compounded continuously. Now keep in mind, if it's compounded monthly or weekly, the answer is going to change a little. It might be 7.8, 7.9, 8 years, 8.1, but it's not going to change that much. There's something called the rule of 72, and perhaps you've heard of it. The rule of 72 tells you how long it takes for your account to double. So here's the equation that you need to estimate it. The time it takes for your account to double is 72 divided by your interest rate as a percentage. So 72 divided by 9, guess what that is? It's about 8 years, which is close to what we have. So that's a great way to estimate if you have the right answer. By the way, if they want you to find out how long it's going to take to triple, simply replace this number with 3. If you want to find out how long it takes to quadruple, replace the 2 with a 4. And then just solve for t. So let's say if we have another problem. Let's say that a bacteria colony doubles every hour. And we want to find out how many will be there, or what the size of the population will be after 4.5 hours. How would you answer that question? If it doubles every hour. Let's say the initial population is 1,000. So first, you need to write an equation. So it's going to be 1,000 times 2 because it doubles every hour, raised to the t. And then all you got to do is plug in 4.5. So 1,000 times 2 raised to the 4.5. And you should get 22,627. That's going to be the size of the population. But now let's say if the bacteria colony triples every 3 hours. Let's say the initial population is still 1,000. But if it triples every 3 hours, we need to put a 3 here because it triples. And it's going to be t raised to the divided by 3 because it triples. This is for every 3 hours. So let me give you some other examples where you could design the equation. So let's say if the bacteria colony, it starts at, your initial population is 5,000. And let's say it doubles every 5 hours. How would you design the equation? It's y is equal to 5,000. Since it doubles, we're going to put a 2 here. But it does so every 5 hours, so we're going to put a 5 here. And then if you want to find out the population after 10, 20, 30 years, plug in that number for t. So here's another example. Let's say if the initial population is 3,000, but it triples every 4 hours. How would you write the equation? It's y is equal to 3,000 times 3 because it triples, but it does so every 4 hours. So if I plug in t for 4, it's going to be 3 to the first power, and then it's going to triple by 3. Now let's say if you get another problem where, let's say the population is 5,000, and let's say the population grows at a rate of 8% every year. What is the population going to be after 5 years? To design the equation, you need to use this. Now, because the population grows 8% every year, you can view it as compounding annually, and for annually, n is 1. So you don't have to worry about n. So p is like 5,000, that's your initial population. R is 0.08, but you got to add plus 0.08, and then it's raised to the t. So basically it's 5,000 times 1.08 raised to the t. It increases 8%. Now let's say if it doubled every year. It would simply be 5,000 times 2 raised to the t. When something doubles, it increases by 100%. So 100%, when r is 100%, basically r is 1. So what we did is we plugged in 5,000 and then 1 plus 1 raised to the t, because r was 1. When something triples, it usually increases by a value of 200%. So you do 1 plus 2, you get 3. And so we just plug in 3. So all of these equations, they really come from this equation when you really think about it. But let's finish the problem that we're working on. So all we got to do is plug in 5 here. So it's 5,000, 1.08 raised to the fifth power. And you get 7,300, and if we round it to the nearest whole number, 47. Now I'm going to explain why r was 100% when it doubles. So let's say if something is 10. 100% of 10 is 10. So you're increasing by 10, so it becomes 20. Thus it doubles. Let's look at when it triples, when we said r was 200%. For something to triple, if we have 10 times 3 is 30, so that means it tripled. But it increased by 20. 20 is 200% of 10. So when something triples, the increase is 200%. So if we use this equation, let's say it triples every not every year, but let's say, yeah, every year. N is 1. We'll keep it simple. So A is going to be equal to, let's say P is 1,000, and then 1 plus 200%, if we divide that by 100, we get 2. So 1 plus 2, N is 1, and then 1 times T. So we get 1,000 times 3 raised to the T. So when it triples, this number is going to be a 3. So that's really where we get that equation from. It comes from this equation. Now the last thing we're going to talk about in terms of word problems for population growth, let's say if the population is 50,000. However, it's decreasing at a rate of 2.4% every year. Actually, let's just say 3%. Let's use a nice whole number. What is the population going to be after 10 years? So we're going to use the same equation. A is equal to P, which is 50,000. N is 1. But because we're dealing with a rate decrease, this is negative. So it's going to be minus 0.03 instead, raised to the 10. So it's 50,000 times 0.97. Notice that this number is less than 1. What this means is that we have a decay problem instead of a growth problem. And then you could plug that in and get the answer. So here's a question for you. This equation, is it growth or decay? Notice that the multiplying factor is greater than 1, so this is growth. If it was like y is equal to 0.95 raised to the t, that would represent decay because it's decreasing. When you multiply 100 by 0.95, you get something less than 100, in this case 95. But what about this example? 2 to the x, is that growth or decay? What would you say? This is growth. We have a positive exponent and a large number. What about y is equal to 2 to the 0.5x? Is that growth or decay? Because 0.5 is less than 1, this is decay. If you were to graph it, it would be decreasing instead of increasing. What about this? 1 over 2 raised to the 2x. Is that growth or decay? This one is decay, because even though it's positive, it's on the bottom. Now what about this? Y is equal to 3 raised to the negative 2x. Even though this number is large, but it's negative, this is the same as 1 over 3 to the 2x. This is a decay problem as well. And finally, what about this example? 1/3 raised to the negative x. Is that growth or decay? Well, because of the negative sign, you can flip it. So this is the same as 3 to the positive x. That's a growth. So sometimes you may see questions like that where it asks you to determine something if it's growth or decay. You just got to find out if it's increasing or decreasing. You can graph it, see if the graph is going up. This will look like this. This will look like that. That's decay. This will look the same way. And this would appear this way. So that is it for this video. We've covered logs, and hopefully this information has been of benefit to you. So thanks for watching.